All right, the purpose of this video is to get you ready for the next day of class related to Lewis structures. And so what we're going to do in this video is we're going to kind of introduce you to some of the vocabulary and some of the ways that we look at Lewis structures and how molecules are kind of put together so that when we get back to class the next day, we can focus primarily on drawing Lewis structures, not just talking about them. So sit back and kind of watch this. There are going to be some questions that correspond directly to the homework assignment that goes along with this particular video. So make sure that you have that open as we go through so that you can answer those questions as well. So kind of looking back to what we saw in lecture the previous day, we looked after this idea of how electrons are arranged inside of the atom and these Lewis dots. And so the Lewis dots, remember, tell us how many valence electrons there are in a given atom. And that gives us some idea about how the atom is put together and what kind of bonding it's capable of doing. And then we talked about electronegativity, the electronegativity scale being when an atom forms a bond, how well does it draw electrons to itself? And that information can be used to figure out, okay, is the bonding, is the electron distribution inside of a substance evenly distributed or is it unevenly distributed? We call that polarity. And we can use differences in electronegativity to kind of help us to determine, oh, are we talking about something that's polar or non-polar, or is it flat out ionic where they're not even sharing the electrons anymore? The electrons actually just left one and gone to the other. So now that we've kind of explored those different pieces, nuts and bolts wise, we want to look at Lewis structures for the different kinds of compounds that exist. So one thing that we need to know is that metallic compounds do not have Lewis structures at all. The bonding that exists there, that metallic bonding, is directly related to that sea of electrons, and there's really no good way of depicting that two-dimensionally. So we're going to focus on ionic compounds and covalent compounds for the rest of this unit. And remember that ionic compounds are coming as a result of the metals and nonmetals interacting with each other. And the metals forming cations, the nonmetals forming anions. And a couple of things that we always have to remember. The net charge has to be 0. And so from a Lewis dots perspective, what we can kind of look at here is we can look at the perspective of, well, if I have one dot here, like I do with sodium, and chlorine is missing a dot, that electron is transferred because this is ionic. And so one literally goes straight into the other. And the net result is that the metal ion completely vacates its valence level, and the nonmetal ion gets a full octet as a result of the transfer. And so that's kind of what Lewis structures for ionic compounds look like. They're pretty straightforward, so long as we are dealing with metal and non-metal ions and not polyatomic ions. What we're going to see is that atoms are going to either gain electrons or lose electrons, and they're going to gain the number of electrons or lose the number of electrons related to how many electrons they need. And so that's ultimately how we end up getting our chemical compounds, is because if I have something that needs 2 electrons, well, it's going to gain 2 electrons to do it. And so how does it go about doing that? Well, it has to collect enough electrons, but it also has to be done in an even kind of sense. So if I have a substance like oxygen, the Lewis structure for oxygen looks like this. So I need a total of 2 electrons for oxygen. Well, if sodium can only give me one, how is it going to fill that other need, that other hole there? Well, it's pretty simple. There's going to be a second sodium atom that comes in to give us the electrons that we need. This is why those substances, that's why sodium oxide is Na2O instead of just NaO. I need two sodiums to supply the oxygens to fill the octet for oxide. So for the most part, these kinds of relationships between ionic compounds and their Lewis structures are relatively straightforward. You know, the metal ion ditches its octet, gets rid of all of its electrons. The non-metal ion adds enough electrons to fill its octet and doesn't take on any more. We can't have any free electrons hanging out in either direction, so we use multiples of one element or another to make it so that every electron gets used. For molecular compounds, it's a little bit more complex than that. We're not talking about a complete vacating of an electron shell. Everything in here is usually non-metallic. And so since most of the stuff here is non-metallic, that does present some interesting issues, because now we're not going to be looking to vacate valence shells. We're going to be looking to fill all of them. And so sharing electrons becomes the way that we do it. And so there are two kinds of electrons in a Lewis structure for a molecular compound. You have these electrons right here. These are known as bonding electrons, and they are shared between the atoms. So each line represents two electrons. And so we can say that with this bond, hydrogen has two electrons and the nitrogen has two electrons from this bond. If I follow it all the way around, I can see that nitrogen has not one, not two, but a total of three bonds. So nitrogen is getting 6 electrons from its bonds. And so how does it get to its octet? Well, that's where these other 2 electrons come in. These 2 electrons are what are called a lone pair. And that lone pair of electrons are unshared electrons. They belong, in this case, to the nitrogen and the nitrogen only. They don't pair up. They don't get shared amongst anything else. They are to themselves. So Lewis structures get a little bit more complicated when we go this direction. And we start looking at molecular compounds. Now, to go about drawing these structures out, there's a step-by-step process that goes into it. Now, I'm not going to go through this process with you step by step. We'll do that when we get into the actual drawing in our next class. But there is a process that goes through here. The first step in the process is we need to determine how many valence electrons there are. We do that by looking at the chemical formula and adding together the number of valence electrons in each element and therefore in the compound itself. We need to determine the center atom. The center atom is going to be the atom that is the least electronegative, that is not hydrogen. And then we start by drawing a simple structure. We put that center atom in the middle. We draw single bonds from the center atom to all of the other atoms, and we make sure everything's obeying the octet rule. And then we do a comparison and we adjust as needed. And so again, not going to go too deep in the details here. We'll hit that when we get to drawing in our next lecture time. But we can go ahead and answer questions like this. So this particular question asks, what is the central atom in phosphoric acid? Well, if I look at my Pauling electronegativity scale, which we covered in our last class, I'm looking at hydrogen compared to phosphorus compared to oxygen. Now, we already know hydrogen cannot be a center atom. Hydrogen is only able to make one bond. One bond doesn't make a center atom. So we're looking at either phosphorus or oxygen, and we can see that the phosphorus is way less electronegative than the oxygen. Phosphorus will be the center atom as a result. So that's how we answer a question like that. Piggybacking off of that concept, if we were again going to look at the Pauling electronegativity scales, oops, I'm on the wrong part. Let's try this one. How many valence electrons are there in phosphoric acid? Well, this is where we would just break out our calculators or do a little bit of simple arithmetic in our head. Each hydrogen has 1. So I've got 3 times 1. Phosphorus has 5 because it's in group 15. Oxygen has 6 because it's in group 16. So 3 times 1 is 3, plus 5, plus 24. 8 plus 24 is 32. 32 valence electrons in phosphoric acid. Now, when we get into the actual drawing component here, this number will become a lot more valuable and reasonable to us. But for right now, we're just kind of evaluating the basics here. All right, let's look at the next thing. How many valence electrons are in a polyatomic ion? Polyatomic ion is the carbonate ion, CO3 negative 2. So we do the same kind of thing. We've got carbon, which has 4. We have oxygen, which has 6. 4 plus 3 times 6. Now, what do we do with the 2 minus here? Well, this is telling us something about the electrons themselves. It's telling us that we have 2 extra electrons. So we have to put that into consideration. So 4 plus 18 plus 2 gives us a total of 24 electrons. Next one here, how many electrons are in this polyatomic ion, C4H9? Well, same kind of thing. We're going to evaluate each element individually. So 4 for each carbon, 1 for each hydrogen. So 4 carbons times 4 valence electrons each. 9 hydrogens times 1 each. What do I do with the plus sign? The plus sign means I have fewer electrons. So I need to take 1 away. 16 plus 9 minus 1 gives me 24. All right. Couple of other things that we want to get into, things that are going to make a lot more sense when we start drawing, but I want to at least familiarize you with the terms now. One of those terms is resonance. Resonance is a result of if I have a Lewis structure that is fundamentally the same, but can be drawn different ways, that's called resonance. And resonance is important because it can actually lead us to a phenomenon known as delocalization, which actually leads to stability. So resonance comes up again when we're starting to draw molecules and the bonding itself becomes arbitrary in its placement. I've got a double bond and a single bond. What's to stop me from putting the double bond on the left versus putting the double bond on the right? Realistically, nothing. And so it's actually not a factor of one of these being correct and the other one not being correct. They're actually both correct and both incorrect at the same time. That double bond actually moves from side to side. The last concept that we want to look at here is something called formal charge. Formal charge becomes important when we have things, these look like resonance structures because we can see the movement of that extra bond, but they're not actually resonance structures. These three structures are different from each other. There's a difference between a nitrogen-nitrogen triple bond, a nitrogen-nitrogen-oxygen triple bond, and having two double bonds on each side. Formal charges help us to figure out which one's the best and which one's not. Now, a couple of things to understand. First of all, these formal charges, they're not real things. They don't actually exist. They're not like oxidation numbers where we look at them and go, okay, well, that tells us what that substance is and how many electrons to expect around it, how it behaves. Formal charges don't do that. They're just a way to help us try to figure out what is the best way to draw a particular molecule. Now, to calculate formal charge, you would calculate formal charge on every single atom in a structure. And the method here is relatively simple. We're going to take, for each element in that compound, we're going to take the number of valence electrons, and we're going to subtract from that the number of dots, so number of unpaired electrons on that atom, and the number of bonds that that atom is making. Ideally, formal charge should be 0. That would be the best case scenario. If it's not 0, we want it to at the very least be low, and we want it to make sense from an electronegativity standpoint. So negative formal charges should go on more electronegative elements. Positive formal charges should go on more electropositive or less electronegative elements. So if you look at those three structures, what you end up seeing is that one of those structures is actually better than the others. This one here, C is actually the worst. C has no formal charges that are 0 at all. And the difference between A and B is where those formal charges exist. Oxygen is a lot more electronegative than nitrogen, so we want that negative charge on the oxygen rather than on the nitrogen. So that's why structure A is favored. So that's all for this very brief walkthrough of kind of these preliminary concepts of Lewis structures and Lewis structure drawing. When we get back to it on our next class session, we're going to apply some of these things to actually drawing, and we're going to go through lots of examples of how to draw Lewis structures so that we can get as much practice as possible and really kind of maximize our ability to do well on these upcoming homework assignments. So that's all for today. Make sure that you finish the rest of the problems in this particular homework assignment, and I will see you next time in class.